Okay. Differentiability and continuity. In this lesson, we will investigate the relationship between differentiability and continuity. Our focus will determine when a function fails to have a derivative. A function that is differentiable at a point is also locally linear at that point. Basically, this is telling us that in order for a function to be differentiable at a point, the graph must be continuous and smooth at the point. Remember, when we say a function is differentiable, this means the derivative exists or you're able to take the derivative. All right, so looking at this, if it's differentiable at a function, that means your left-hand limit of the alternate form and the right-hand limit of the alternate form have to exist or have to be the same at a finite value. So, or you could think of it as the limit of the derivative, right? That's what we're talking about here, yes? The limits of the derivatives have to be the same. All right. How f prime of a may fail to exist. The following examples will show us how a function will fail to have a derivative at a point where there is a corner, a cusp, a vertical tangent line, or a discontinuity. So let's look at this. Example 1. Given the graph of f of x equals a, what is the f prime of x, or the derivative of f of x as x approaches 1 from the left? Well, we got to think about that, don't we?
Slope is -1.
Right, so that's what we're looking at, is the slope, yes?
Mm-hmm.
So the slope will be -1, so our slope graph would be from 1 to the left would be at -1. Do you agree with that?
Mm-hmm.
So your slope would be at -1 here. And the slope here, as it approaches 1 from the right, is
1.
+1. So this would be something like this, correct?
Mm-hmm.
From 1 to the right, your slope graph would be to the right. Isn't that the graph of our derivative? Yeah? If f is continuous, is f continuous at x equals 1? Does it continue?
Yeah.
Yeah. But is it differentiable? Was this true?
No.
Did the two limits equal each other? So no. And then we'd have to justify. So since the limit as x approaches 1 from the left of f prime of x does not equal the limit as x approaches 1 from the right of f prime of x, there is no derivative. So that's that justification piece that we always have to do with free response, right? Given the graph of f of x equals the cubed root, the cubed root of x, use the alternate form of the derivative to show that the function has a vertical tangent line at x equals 0. Well, let's use the alternate form. So we're talking about when x is 0. So the limit as x approaches 0. And if we're using the alternate form here, f of x is the cubed root of x minus f of c. Well, c is 0, isn't it? So we're talking about the cubed root of 0 over x minus 0. So we can simplify that a bit. That'd be the limit as x approaches 0 of the cubed root of x minus 0 over x. Or what I'm going to do is I'm going to rewrite it with rational exponents. So this is the same thing as saying x to the 1/3 over x, and that makes it a little easier to simplify. You could have instead like multiplied by the cube root of x squared over the cube root of x squared and done it that way. But if you change them to rational exponents, now you can just subtract those rational exponents, and we'd have the limit as x approaches 0 would be, the bottom one is higher, isn't it? Because that would be 3 over 3. And so that would be 1 over x to the 2/3. Well, if we plug that in, you'd have division by 0, wouldn't you? And we can't have division by 0. Therefore, the limit is undefined. So our slope would be undefined, which right there you can kind of see that, can't you? Make sense? All right. Example 3. Given the graph of f of x equals 1 over x plus 2 squared, describe the derivative of f as x approaches negative from negative 2, from the left and from the right. So, as x approaches negative 2 from the left, what is your derivative approaching? So that means we're looking for the slope, correct?
It approaches a very positive.
So, yeah, let's look at this. This one here, it's getting really, really big there, isn't it?
Mm-hmm.
Your slope. So it's going to be approaching a positive, really large number, or positive infinity. Do you agree with that? And as x is approaching negative 2 from the left, this one, your slope, thinking about this one here, it keeps getting bigger and bigger and bigger, but it's a negative, isn't it? So this slope, as we approach here, is getting larger, except for it's actually getting smaller because it's negative, yes?
Yes.
So that would be approaching negative infinity. Do you agree with that?
Mm-hmm.
So those are not the same, nor are they real numbers. So f is not differentiable. At x equals negative 2. Make sense?
Mm-hmm.
B says given the derivative f prime of x equals, so it gave us our derivative function. Use the formula to evaluate the derivative when x is negative 2. Well, we're probably going to have to do that from the left and the right, because we know that if you plug in negative 2 there, what happens? You get 0, don't you?
Yeah.
Because negative 2 plus 2 is 0. So let's think about this. The derivative as of negative 2. Now we're going to have to do an approximation here. So if I'm approaching negative 2 from the left, and I should probably put that in there, from the left, I'm going to plug in some number that is to the left of negative 2, but really close. So maybe like negative 2.1. That'd be to the left, wouldn't it? So we're looking for the behavior here, because we know it's not going to be a real number. So that's going to be something like negative 2 over, what, 0.1 cubed? I don't know why I put a 3 there. That should be a 2. So negative 0.1 cubed. So what I'm seeing is I've got a small number, a negative number, over a really, really, really small number. Yes? Which is also a negative number. And a negative over a negative becomes a positive. So we're talking about a small number divided by a really, really small number. So what are we going to have here? It's going to go to infinity, isn't it? And it's positive because a negative over a negative becomes a positive. All right. Then let's think about that from the right. So here we could plug in what, negative 1.9? That would be to the right, wouldn't it? By getting closer. So negative 1.9 plus 2 cubed. So here I'm going to get a negative 2 over a positive 0.1 cubed.
It's like 15 or
So a negative,
so. Oh, negative, yeah, sorry.
so a negative over a positive really small number, where's that going to be going to?
Negative.
Yeah. So we're talking about the behavior there. It's not an actual equal sign because we're not talking about that it's equal to that. We're talking about a behavior there. So we could say the derivative of f at 2 does not exist. Because neither one of them are going to a real number, and they're definitely not the same, right? All right, this is so important, guys. Differentiability implies continuity. So if f is differentiable at c, then f is continuous at c. However, it does not go the other direction. So differentiability does imply continuity, but continuity does not imply differentiability. Because of the sharp corners, the cusps, the vertical asymptotes, discontinuities. All right, write a contrapositive statement. If a function is differentiable at x equals c, then the function is continuous at x equals c.
It's been a while since I've been contrapositive.
Right? So what are we talking about? Right here, we don't have any negatives, right? But 2 negatives make a positive, don't they? So that would make it positive. Contra means we've got to say the opposite. So how about if
a function is not differential,
is not continuous?
yeah.
At x equals c, then f of x is not differentiable. At x equals c. So those say the same thing, don't they? Kind of. If it's differentiable, then it's continuous. If it's not continuous, then it's definitely not differentiable. But just because it's continuous does not mean it is differentiable, right? But if it's not continuous, it's not differentiable. We get that? Okay. I think the bell's getting ready to ring.
It's 45.
45 is when it rings. And so,
45 right now.
and what time does the bell ring?
15.
Oh, we got 10 minutes. Let's finish this one problem. Describe the x values at which the function g of x equals the absolute value of x squared minus 5 is differentiable. Justify your answer. So we need to look for where the problem areas would be concerning, right? And so they give you the graph, and you can see where that would be true, where those would be concerning. But we know that absolute value kind of creates a V, or it turns the negative values positive, right? So if we just had x squared minus 5 or negative x squared minus 5, we know that'd be an upside down parabola, and we got to flip the negatives to a positive, right? So everything here that's below flips upside down, yes? So we know that we're going to have corners where what's in absolute value is equal to 0. Do you agree with that? So our areas of concern, or problem areas, are what we need to look at. So our problem areas are when what's inside of absolute value is equal to 0. So that means that when x is equal to the plus or minus square root of 5, do you agree with that? You'd add 5, take the square root of both sides. So those are our problem areas. So it wants to know where it's differentiable. Is it going to be differentiable at those sharp corners?
No.
No. You can think about your slope graphs, right? That's not going to work. So it's going to be differentiable everywhere else though, right? So it's going to be differentiable from negative infinity to negative square root of 5. It's going to be differentiable from the negative square root of 5 to positive square root of 5. And it's going to be differentiable from positive square root of 5 to infinity, just not at those exact points. And then we need to justify, so I would say something like, since g of x has a sharp corner, or not a, it should be more than one, right? Has sharp corner or corners or cusps at x equals negative square root of 5 and x equals positive square root of 5. It is not differentiable here. Or there. Or we wouldn't have even had to say it's not differentiable there. We could have just said this, since g of x has sharp corners at those 2 points. So we wouldn't even really have needed that, right? Does that make sense? Questions? Let's go ahead and look at example 5. Find all the values for x where the function is differentiable. Well, in order for it to be differentiable, we need it to be continuous. Do you agree? Mm-hmm. And so we could figure out whether it was continuous by looking at these two when it's at 0, yes? And then these two when it's at 3. Do you agree with that? So let's look at 0. In order for it to be continuous, we need x plus 1 squared to equal 2x plus 1 when x equals 0. Do you agree with that? So let's see if this is true. If we plug in 0, we'd have 0 plus 1, which is 1 squared. And here you'd have 2 times 0 is 0 plus 1. So is it continuous there? Is the left side equal to the right side? Yeah, because when this is 0, it's equal to 1. And when this is 0, it's also equal to 1. So it's continuous at x equals 0. Now at 3, we're talking about when x is 3. Let's look at that one. So we need the left-hand side, 2x plus 1, to equal the right-hand side, 4 minus x squared, right? Well, if we plug in 3, 2 times 3 is 6 plus 1, which is 7. And if we plug in 3 here, we would have 4 minus, 3. 4 minus 3 is 1 squared, which is just 1. Do you agree?
Mm-hmm.
Those are not equal. So it's continuous at 0, but it's not continuous at 3, correct? Okay, well, now that we know it's continuous at 0, we got to see if it's differentiable at 0. So yeah, we've got it continuous, but now we got to figure out, is it differentiable? So at 0, at x equals 0, in order for it to be continuous, we need to know what the derivative is going to be. Do you agree with that?
Yeah.
We could sketch a graph quickly and look at that. So here, this is a parabola that has moved, what, to the left one? So we know our vertex would be here, and we're talking about at 0, so this would be like this. Do you agree with that? And then this, we said that when x was 0, it was up at 1, and it would have a slope of 2 over 1. So it's going to be a straight line going like this, correct? Oops, except for it does end. It ended when it was 3, it ended at 7. You agree with that? So it ended up here at 7, and it was an open circle. And then this piece is a parabola, and it would look something like when x was 3, we were up at 1. And it was a closed circle, so it'd be something like this. Yes? So, let's go ahead and finish it. As x is approaching 0 from the left, the derivative at 0 is what? So as x approaches 0 from the left, what is this slope?
It is 2x.
It's 2, right? And as x approaches 0 from the right of the derivative, what is it going to be? The slope is still 2, right?
Yep.
So is it differentiable there? The left and the right were the same, yes? So we're good. So the limit as x approaches 0 from the left of the function was 1, and the limit as x approaches 0 from the right of the function was 1. So this deals with our continuity. This deals with our differentiability. We don't have to deal with the differentiability of 3 because we know it wasn't continuous, right? So our conclusion would be something like h of x is differentiable at what, everywhere except for 3. So negative infinity to 3, union 3 to infinity. There is a discontinuity at x equals 3. So h of x is not differentiable at x equals 3. Something along those lines. So we couldn't stop at it's continuous, right? We had to go on to, okay, it's continuous, now is it differentiable? We could stop at it's not continuous. All right, we'll continue on next time.